Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today, basically, I would like to tell you about some counting voodoo. Counting voodoo is always fun. So, kind of miracles that happens if you just play around with certain functions. And the function would like to play around with today is the variant of the famous Riemann Zeta function. So, kind of Zeta functions. Well, the Riemann Zeta function is certainly the first one of its kind, but there are quite a few of them known nowadays, and I will discuss one of them, and it's related to some discrete mathematics, so some languages, some logic type mathematics, computer science, whatever you want to call it. And it's kind of really uses a lot of those properties of zeta functions, which are really a little bit magical. Like you play around with it a little bit, you shift symbols from left to right, and in the end, there will be a nice formula that pops out. And well, because it's discrete mathematics I'm going to discuss, it's something like one counting problem is equal to the other, which is not really obvious at all. So counting voodoo, that's what it's all about. But let's get started with the classical zeta function. So here is a copy or a screenshot, actually, of Riemann's famous paper, where Riemann defines the zeta function or uses the zeta function and has this funny expression here, which we'll see several times, not in the setup of the original zeta function, as I said, but more in the setup of discrete mathematics. So basically, it's the following idea. Whatever it is, you have some complex variable s, doesn't really matter, some variable s, and you have the sum here. And not in Riemann's paper, but not hard to show, is that there's an exponential version of this sum, which I'm not going to explain. It's not so important. There are some logs involved, some n to the n minus s. We will see something very similar. And a fun Mongol function. Whatever that is, doesn't matter. There's an x expression for it. So here's an x expression. And then there's Euler's famous identity, which is this product type expression, product over blah, 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 whatever, 1 over, 1 minus p to z minus s or something. Yeah. And so an exponential equals a product, which is kind of pretty cool, actually. Obviously, the zeta function is around in mathematics for a long, long time. So this was around 1850. And kind of the magic here, which is then not just, so zeta function usually analytic number theory, which is then just not just analytic number theory, is kind of playing around with those symbols, and some funny identities pop up. And people have discovered that, of course, a long, long time ago, and then start playing around with, as I said, just these abstract properties and define kind of discrete versions of the zeta function, counting various things, and I would like to focus on one of them. But it's really just really motivated, as we will see, by this funny expression here, which is kind of turning an exponential into this product, which is absolutely not obvious. For example, it shows that's exponential here. Ignore that s is a complex number or whatever. That's exponential here has this nice expression. In particular, it has some kind of integer coefficients, which is not really obvious from the exponential expression at all. From the other side, you just expand it, kind of Taylor expansion, and you will see that it says integer coefficients. Very good. So this is kind of the starting point. As I said, kind of makes sense. In hindsight, it's pretty obvious, but of course, someone came up with it before. It's around for a long time, so I don't quite know the first example of the following kind, of this discrete zeta function type kind, but certainly people have played around with abstract properties of the classical zeta function for a long time, right? So that's kind of the point. So this identity kind of goes back to Euler, as you actually written here in Riemann's paper. Okay, so I would like to apply it to a very discrete part of mathematics, maybe even to computer science, depends a bit what you call it. So I would like to use formal languages, and I will tell you in a second what a formal language is. But basically, it's this beast here. So you have an alphabet, so that I call it A, and it's just the numbers you would like to use, or the symbols you would like to use. So binary, you would like to use 1 and 0, for example. Apparently the Roman alphabet has those numbers, decimal, whatever, special characters, the keyboard characters, the genetic code, apparently the protein code as well, just some symbols, and you stack symbols together and you get certain things. So the symbols have sometimes names, but it doesn't really matter. So the elements of my set are just the symbols my alphabet. And whatever I stick together is basically these are the words in my alphabet. So 0, 1, I can stick together as much as I want, and I get whatever kind of expressions of this form. A little bit more complicated for the other ones, but all of you know how keyboard, for example, works, right? So you can construct words. Just the notion of a word is really weak here. So it doesn't need to make sense in English or whatever kind of language you're using. It just needs to be a concatenation of symbols, and that's a word. So the elements of this formal language are called the words, and the formal language is then, if you want, mathematically described as a free monoid, as a subset of the free monoid on the alphabet. So you might actually not take all words into account. You might just take a subset or whatever. But basically, you have an alphabet and you form words in it, and that's your language. That makes sense, right? No language. You have alphabet and you have words. So languages are very important in everywhere, basically, but they originate in computer science, binary language, or whatever kind of language you have in mind. But as you can see here, they're not restricted to mathematics or computer science. So DNA, you could think of it as a language, which is a pretty cool idea, actually. And apparently protein codes, you can think of it as a language as well. So here you go, examples of languages, which are kind of real-world examples, if you call DNA a real-world example, of course. And you can define a zeta function for those languages, which is already a pretty cool idea, because I said you wouldn't have come up with that. And as you can see, it looks exactly like the X expression we've seen before. So here it's exactly the X expression. Something funny is going on. Here we like negative exponents. Here we like positive exponents. Whatever. S to the n. And it looks a little bit different, as you can see, but it's still basically the same. Anyway, so let's come back to it. As you can see, it's slightly different. Say it again. Let's compare again. So this is slightly different, but kind of the same idea. You have an n to the minus s, and here you have a s to the n, and some counting. The counting in front of this function was given by this, von Mongold function, basically. And here we like to count the number of words of a given length. Okay, so we form this exp in the number of words of a given length, and take s to the n and have this expression that we call the zeta function of the language, and s is some formal parameter. Doesn't really matter what s is. So let's do some examples. So wn just, as I said, counts the number of words. Right? So that's a counting here we like to do. So the easiest language, which is not completely boring, is probably the language of binary strings. So I only use symbols 0, 1. So words are sure. So empty word, never forget the empty word. You could say nothing. That's a word as well. So empty word, this is supposed to be an empty set. And then, of course, 1, 0. This is a nice one, right? This is a perfect one. Let me try again. 0, 1, and then for something 0, 0, 0, 1, 1, 0, 1, 1, and etc. Right? So the number of words, it's really easy to count here. It's really just 2 to the n. So 1, 2, 4. The next one would be 8. That's not so hard to count. In this language, it's really, really easy to count. So actually, our function will look like this funny exp. And if you Taylor expand this function, and this is kind of the idea. So the Taylor expansion of this function gives you kind of the generating function of the words. So 1 plus 2s plus 4s squared plus 8s cubed. So here, words of length 8 are just encoded in the coefficient of s to the 3. S, as I said, a formal variable. Words of length 5,000 would be encoded in, whatever kind of coefficient is in front of s to the 5,000, right? So you have a generating function for those number of words for a given length, and just given by Taylor expansion, which is already pretty cool. But right now, it's basically just the Taylor expansion, the generating function idea. And it's not quite clear why we actually don't just write down this expression to begin with, but why we have this funny zeta type function here. And the theorem is then the Euler expansion of the zeta type function. So let us go back. As I said, the details, how they look like, are a little bit different. But basically, it's again this one here, right? You have this exp, and the exp is equal to the power of the product of these primes. And here it looks very similar. It's the exp, and the exp is equal to this product, this infinite product. And now our counting drastically changes in some sense. And this is then the magic here. that the counting number of words is the same as counting those conjugacy clauses, which I'm going to explain in a second, linked by the zeta function identity, that the zeta function is equal to the product. So the Euler identity, whatever you want to call it. And here the count is what I call CN, which are conjugacy clauses of primitive elements. But sounds much more complicated, but it's actually not so hard to count. So primitive just means it's not a proper power. So in our language from before, for example, 0 is not a proper power, well, but 0, 0 is, because it's just 0 squared, yeah? Right, so that's a not proper, so primitive, not proper power, like a primitive root if you want, and otherwise you don't care. And conjugate is really just the following. So you have something like 101, and you're allowed to cut it and put this on the other side. So can I do this? 001. So I've cut it here and put it on the other side. And these are then conjugate words, right? So cutting and moving things around. If you like to think of these things as just sitting on a string, so those numbers, those elements here, whatever, 000, they sit on a string, and conjugate just means you can push it around the necklace or whatever you want to call it. And everything you see is the same. And here would, for example, I would read from top to bottom or whatever makes sense. So 0, 1, what is it? 0, 1, 0, 1, 0, 0 is equal to all of its conjugates. That's the name. That's why. And you call as you call, absolutely you call. You count those primitive words of certain lengths. Okay? And it turns out that this is exactly the correct count. This is what you need to do. And you have this funny identity, which I've done here in an example for this example. So instead of having this identity, you can also write it as this infinite product. And if you would expand the infinite product, you would get the corresponding expression that you see on the other side. And it's kind of a funny matching of counting, something that looks really, really different. Counting number of words or counting those conjugacy clauses in the language, which is pretty good. So the theorem is pretty cool. It has this one restriction that you need a cyclic language, and cyclic basically means, well, you have this necklace property. So whenever you have a word, you also have all of these necklace conjugates, right? The reading order doesn't matter. And you have this root property. So if you have something like 0 to the n inside of your language, then you want 0 to be inside of your language as well. But anyway, up to this slightly, well, it's not so bad. It's not a huge condition. Most nice languages will satisfy it as well. Anyway, as well. But that's the point. So if you, as soon as you have a cyclic language, you get this Euler expansion, a zeta type function identity, which is pretty cool. I mean, just something very different than the classical one, but basically very similar in flavor. One of the prime numbers and some complex functions, and you just pull them around, push symbols around, and you get the identity. Euler did that. Euler was, by the way, a master of pushing symbols around. Brilliant. This is just a discrete version of pushing symbols around. That's pretty cool. It's pretty cool. Not so hard to prove. Link is in the description for the original paper. Relatively recent, from the 1990s. And this is really a strong theorem because it applies to any cyclic language. So let me just tell you how to construct many cyclic languages. And it works as follows. You just take a graph, G. No, I decided to count my graph gamma. So let me call the graph gamma instead. Why not? Doesn't matter. So here I have a graph and it will have some edges, A, B, C. Right? And just running around the graph will define for you a word if you want. So A, B, C, I could read off A, B, C here, but I can't read off, for example, CBA, right? CBA, I can't read off CBA, but otherwise any graph defines me a language. In order to make it cyclic, there's a really easy trick to make it cyclic. You just double all the edges. So here we have an edge in this direction, so we just add an edge in this direction with the same symbol, and then we can just read out all language. So we could now read out this expression here. So any graph, double the edges. There will be some labels on the graphs that these are your symbols, your alphabet. This will define your language, right? So any graph defines your language. That's a huge reservoir of languages. And for all of them, the magic theorem applies. So counting words, like counting paths in the graph, is the same as counting these funny conjugacy clauses related by the Euler type function, right? The Euler type identity. Which is pretty cool. So it's actually a really strong theorem. Two counting problems that are related in a very deep sense, which really do not look related at all. But in the end, they're actually related. So yeah, I hope you enjoyed this counting voodoo video. As I said, this is kind of just the tip of the iceberg. There are many of Zeta type functions for discrete situations. This was just the one I could easiest find and explain. Hopefully it wasn't so bad, just languages, just stacking words, and you just count different things. You either count those conjugacy clauses, or you just count a plain number of words, and they are linked by this extremely funny identity, which is, let's just say, exactly the same, which is not quite true, right? Exactly in huge quotation marks, exactly the same as for the classical Riemann Euler identity of the Riemann zeta function, which is, I think, a pretty. Anyway, I hope you enjoyed the video, and I also hope to see you next time.